Okay, so thank you very much for inviting me through the foundation, especially the sponsors, Mr. Milner and Pete Warden for the introduction, and many other people that I have interacted this way these days. Apologies also because I'm always late submitting things and posting things on the websites. It's just the semester was ending and we had a lot of work to do. Anyway, I'm very excited to be here. I'll be telling you a bit about Proxima Centauri. Oh, there's a... Yes, okay, that was my fault. Basically, the title of my talk, it's a bit different from the talks that I have been given recently. I've been explaining as many places as possible how we find planets, why we are finding the planets that we find today, why red dwarfs, for example, are so much in the spotlight, and why we are not looking at sun-like stars, which we all love. We love sun, like the one here in California. There are a number of reasons for that. There are a number of historical reasons especially, and I'll try to lead you through that. There will be other talks later. I wasn't sure which ones we're going to be talking about, but apparently there will be current addressing, talking later about occurrence rates of planets around M-dwarfs and some other techniques, and even habitability, so I don't need to spend much time on this. So I'll try to give you a bit of the context of why we are finding these planets, why we focused on Proxima, and what are the expectations, especially for this very nearby stellar sample where we eventually want to go. What are the techniques, the leading methods that are giving us more information, at least in terms of detection of planets, and what information we have. Because the detection is just the first step. We know very little from these planets. I assume that the audience is not only professional astronomers, so I apologize if some of the concepts are a bit basic for some of you, but I think it's interesting that we actually, at least on the first talk, we set a common ground for discussion and put some things in context first. Okay, so let's move on. First, this is the summary of my talk, so I could just show you this, and we would be done, because this is all we know about this planet. Let's say planet candidate. We are pretty convinced it's there, but you never know. Things can go wrong for a number of reasons, but it doesn't matter. Let's assume the planet is there. You have measured the motion of the star, as you will see. That's the method called radial velocities. You measure that the star is going back and forth by 1.4 meters per second every 11.2 days. So you measure this wobble over time, and then doing very basic math, you get that this is consistent with a planet orbiting the star, with 1.3 Earth masses, minimum mass, very close to the star as well, and receiving more or less the same energy the Earth is receiving from the sun. So that's all we can know. Everything that comes after that, if this is habitable or not, or what kind of atmosphere, or what kind of planet it is pure speculation. Some of this is well educated, but we don't know much about it. And that's a bit of pity. You will see some planets that we actually can learn more about them. These are the transiting planets, but for a number of reasons, it's almost not impossible, but you will see it's very hard to find transiting planets around this very nearby sample. Anyway, it's everything part of the same edifice or building of knowledge, as you will see. And the reason why we found Proxima b this year is actually because we have accumulated a lot of knowledge from other missions, from experience, from other surveys that led us to be able to formulate a proposal to sample this star in a very special way that allows us to detect these planets. The technology to detect these planets has been there for almost 15 years. This could have happened in 2002. It didn't happen not because the people that were using the telescopes at the time were stupid. I will never claim that. What happened is that we didn't know what to expect. At the beginning, it was like fishing, like going into a forest and trying to find something. You don't know where it is. Now we know where these planets are, so we know how to find them. And we have improved a lot in recent years, especially in the strategy to identify and point it out. So that's what I'm going to try to communicate here. Let's see. Very quickly, so it's the Starshot initiative. This is something I want to show always, all the time when there's a general talk. There are specialists here, I know, but even for an astronomer, it's difficult to grasp what are interstellar distances. So this is a simple exercise, mindset. This thing here is a pizza, but that would be the solar system. The orbit of Neptune would be the outer border of this pizza. The orbit of Jupiter would be the inner slice of a pepperoni piece. So if that's the solar system, where you would put Alpha Centauri in this landscape? Would be across the street, would be in the entrance of this village, would be in the faraway forest, or in the mountain in the back. Anybody wants to guess? Yes, so, well, in the mountain in the back, here, if this is the solar system, and this is about 20, 30 centimeters, Alpha Centauri is at 3 kilometers from this. So you can get a sense of perspective. You have a plate in front of you, look at the feature. At 3 kilometers, this is interstellar distances. So it's not a little bit farther away. It's 3 orders of magnitude farther away than anything that we have tried before. So when people ask you, oh, how we are going, how many years it will take us to go to places like this, you have to remember them that this is not about a stroll or a longer stroll that's just going to Mars. This is a completely different story, and this is not going to happen tomorrow. OK, good. So we know where we are, Alpha Centauri, and the sun here. And now that we are talking about nearby stars, let me show you a plot. That's a nice picture prepared a few years ago by Todd Henry and his group in Georgia State University that shows us, in this diagram, what you have is the sample of the stars within, oh, perfect. Well, anyway, I think it's better I walk. It's a sample of the stars within 10 parsecs, about 30 light years. And what you can see is that our sun, which I call Sol here, this is a green, a yellow star. It's actually top 20% in mass of the solar neighborhood and also in the galaxy. The sun is a very massive star. Most of the stars are not sun-like stars. Are these small things called red-dwarfs. And this has consequences. Is one of the reasons why we are finding planets around them, because we have many more targets actually available within reach. Just very quickly, to give context, this is just a picture of the solar neighborhood in 3D. This is 25 parsecs. As you see here, most of the dots are red, because these are the red dwarfs, so many more than regular yellow and other more massive stars. And again, just to put things in context, we are in the spiral arm of a galaxy. And here, our neighborhood, not the solar system, the solar neighborhood is a pixel in this picture. OK, so we know our first take-home message is that most stars are red dwarfs. Good. Now, we are interested not only on the stars. Stars are nice, but we want to find the planets. So how we do that, finding planets, at least taking pictures of planets, is complicated. And I'll try to illustrate it here very quickly, because most of you are familiar with the problem. Here we have a star, nearby one. This is the closest single sun-like star. This is Tau Ceti at 11.9 light years. This is just the moon for scale. And we are trying to see the planets around this star by just zooming in. Right? So we zoom in, and what we see is that thing that looked like a small point with our telescope, it looks larger now. Even though it's still a point source, the star, what we see is a blurb, and this is coming mostly from the atmosphere, but also from diffraction from the telescope. And in this blur here, at some point, we should see that pizza that we saw before, right? The thing that tells us that there's a planetary system there. So do you see the pizza here? I don't. So if you zoom in, now you see it here. And you can see the problem. So if you want to try to image something that is around this small circle in the center, you have to get rid of all this scattered light, diffraction from the atmosphere. Even if you go from space, you have diffraction, you have reflection, you have scattered light from your optical components. For every photon that arrives from the star, from the planet, there will be 10 to the 9 photons arriving from the star. And you have to separate them to be able to take a picture. So getting pictures of planets or detecting them directly is complicated. Instead of that, we have a number of indirect methods, or there's also a direct method here, direct imaging, what I was talking about. But the ones that have been more successful so far, not only successful in terms of finding planets, but also telling us about populations, what kind of planetary systems are out there, are the first two, the velocity method and the transit method. I'm not going to go into a lot of detail, but because there will be talks about especially the transit method later. But it's important to know what the transits have told us, or at least the take-home message that we need to take from the transit observations. So I'm not going to talk about a lot of transits. You know what it is, how it works. You have a star, you have a planet going in front of it, you have a small dip. So you see this repeating over time, and from the size of the dipness and the time it takes to repeat, you get the orbital period and the size of the planet. Good. So the problem with transits is, of course, the planet needs to be aligned to our line of sight. That's, for example, a case in top of this, but for each planet that we detect, depends on where you put the planet and a number of things, but just quick numbers. For each planet we detect, basically we only detect 2% of the planets that are out there. So for each one that we see, there will be 50 of them that will be hiding in some just strange orbital inclination. Now, if we only detect 1 every 50 planets, and the solar neighborhood you saw at the beginning has 300, 400 stars, so we expect that by transit observations, we would measure or we would detect about 6, 7, maybe 8 transiting planets around this very nearby stellar sample. So the transiting method is very good. It gives you full of information, and it will be probably the one that will give us the first probes to the properties of these planets in a lot of detail. But for when you're really limited to a sample of stars, especially the nearby ones, it's not really the most efficient one. OK, so just a quick, one of my favorite Kepler result plots that shows us something important about planetary systems is that this is Kepler detections in 2015. This is size, Earth radius. This is orbital period, which is the same as semi-major axis, more or less. And what you can see is that there are a lot, and this includes all spectral types, so unlike stars, M-dwarfs, everything, there are a lot of Earth-sized planets in these warm or hot orbits if the star is sun-like. But this is more or less independent, actually, of the spectral type. You can see these planetary systems very compact, also around K-dwarfs and also around M-dwarfs. And now you have this combination of a lot of planets in small sizes, close to the star. The star is cooler, so these planets will be warmer. And that's kind of the missing element that was needed to start to heavily look in detail to each one of the stars that we have in our solar neighborhood. 10 years ago, we didn't know that. Nobody suspected that there were compact planetary systems. So you write a proposal to a telescope allocation committee, and they would say, OK, this is a waste of time. It's much more secure to make a survey with a lot of time allocation to look at 100 stars instead of going one by one, because we don't really have a clue of which planet you are expected to find. Now that has changed, and that's a major difference in the last 3-4 years. And that's what enabled these very focused campaigns, especially on these red dwarfs, because now we are talking about Earth-sized planets in short period orbits, which gives us another advantage, as you will see, and that are warm and have the potential, especially if they transit, to get some further characterization. OK, so that's a take-home message too. Most stars have small planets in short period orbits, including M-dwarf stars. Now, let's talk very quickly on the radial velocity method. That's the one that we used to look for planets around Proxima. That was also the first method that was used to detect planets. Radial velocity method, basic physics is that you have a planet orbiting a star at the center. The planet and the star orbit the common center of mass. Because the star is more massive, it moves less. So it makes this small circle. When the star comes to you, the light gets blue shifted. When the star goes away from you, the light gets red shifted. So by measuring this wobble, you can infer, first, the orbital period, because you know how often this pattern repeats, this motion, going back and forth. And also, you can infer the mass of the planet, because the larger the planet, the more amplitude, the larger will be the motion of the central star. Good. So measuring radial velocities on stars is challenging, and this is just an example. Here, this is a typical spectral line of the sun. Here, that would be if you had two sun-like stars, one moving 15 kilometers away, the other one coming 15 kilometers towards you. So you would clearly see two spectral lines. It would be very easy to detect binaries. This is how in the 20th century binaries were detected, just by looking at double-lined spectra. And now when you have a planet and the motion is much smaller, it's not 30 kilometers, but it's 300 meters, you barely see it here. And we don't want to measure things at 300 meters per second. We want to measure things at 1 meter per second level to detect planets. And this is what you see. That's 0, and that's 3, right? So that's the motion that you have to measure. And basically, we are looking here at the tip of this line. So this is very hard to see, especially because this would be perfect data. But actually, the observations are way worse. This is high signal-to-noise spectra. These are points, data points that would be a very high-quality spectrum. And now you have to fit for this tiny, tiny motion with these huge error bars. So how you do that is not only look at one line at a time, but you look at thousands of them. This is the spectrum, a shell spectrum taken, I think, from Peck by Paul and Jeff Marcy a few years ago, and you can see a lot of spectral lines, and basically, in this spectrum, I think there are about 1,000 of them. Basically, what you do is put the whole spectrum and see how it shifts over time, calibrate it very well against a laboratory standard, can be iodine, can be a thorium, argon lamp, something like this. And at the end of the day, you can get very high precision. Good. So that's what you do when you try to detect a planet. This is an easy one. This is a gas giant planet, as you will see. You go to a telescope, you take some spectra, you measure some velocities. Looks like the star is coming to you, minus 100, at 100 meters per second. Then you go after a few months to the telescope again. It looks like the velocity of the star is changing. You go again. Now the velocity of the star keeps changing, so there's some acceleration over time, but nothing happens. So it might be a binary. It might be some acceleration from some object that we still don't know. But after a while, and you have patience, then you get that the star starts to come back to you. And this is a planet detected by the Doppler method. It's a massive planet, amplitude of 100 meters per second, but a period of 3 years. So that would be a classic gas giant. Very nice. This is a plot of kind of the timeline of the planet detections masses of planets detected with the radial velocity technique. As you will see here, we have 51 Peck, discovered by Michel Mayor and Didier Queloz. Now, in the next year, you have Marcy and Butler realized that they had a ton of data, but they didn't analyze it thoroughly enough because a number of things. That's a story for another day. And then the next year, they published 5 planets that they had in their data. The next year, they published nobody, because I guess that they found all the planets that they could find in their own data. And then the race for exoplanet detection started to ramp up. Lots of gas giants detected here. The new instrument started to operate in 2000. That's Keck with new iodine cell. That would be HARPS. Some other instruments started to operate as well, not specialized instruments, but still be able to do some planet detection. And at some point in 2010, you can see that the detection hit a kind of limit. And that has to do with the fact that first, the instruments that we are using in 2010 are still the same as in 2000, because nobody built anything really new in these 10 years. Of course, there are improvements and refinements, but nothing really revolutionary. And also, because we hit the stellar noise. The stars are variable by themselves, so you are not only limited by the precision of your instrument, you are also limited by how the stars are varying. So it's difficult to interpret the variability you see as planets. And that's basically what made this curve stop here. We got lucky in a sense that then in 2010, 2011 is when people really started to focus a lot on M-dwarf stars. And basically, all these planets that are low mass here, these are coming from M-dwarfs, red dwarfs. So one of the mass planet that would be Proxima B here. There are a few more here. But again, the detection is now limited by stellar noise. The problem is that how depends on who interprets the data. There is no really consensus model because we don't really understand stars at the level that we need to interpret the radial velocity measurements. We don't even understand the sun at that level. So there's a lot of work going into this. So we hope to be able to get better than this. Also, instruments need to improve a bit. But for now, let's assume that we are hitting this noise floor, and that limits the precision of Doppler measurements. So when you do that, then is when then you start to go into complicated statistics. This is only a formula I'm going to show you, I promise. So basically, what we are trying to do is say that the measurements that we have is a sum of different terms and try to correlate these measurements with chromospheric activity, with changes in the line profiles, with changes in the magnetic activity of the star, things like this, and hope for the best that you can isolate the signal that's coming from the planet that cannot be interpreted any other way. That's method number 1 that you can do. Method number 2 that you can do as well is that there are things that you really don't understand of this variability. You put them in some fancy data analysis technique that's called Gaussian processes, basically measure this variability that's quasi-periodic in terms of correlated noise. This has some problems because sometimes planetary signals, and especially if there are more than one, and correlated noise look the same. But typically what happens is that what you try to do is do this, also do this, and then you find that there is something maybe convincing that might be a planet. So then you try to get more data. And this is what we tried to do in this campaign, the one that focused on Proxima. That's a pale red dot campaign. And basically, is this exercise. We didn't plan it a priori. It looks like we were very clever and we very formal. This didn't happen this way. We just improvised as the data were coming. OK, this is not working. You have this correlated noise. I don't believe the result. So it took quite a number of years to to have all this process kind of streamlined. Also, a lot of papers, controversies, and things like this, but I think we learned a number of things on the way, and basically we implemented them in this campaign. So the point is you have all this data collected in an optimal way. You have all this activity data, photometry for many sources. You think there is a signal there. If you really want to claim that something is a planet, you need to design an experiment to be able to either rule out or confirm it. Because just taking data and putting things together outside without making a prediction, if this is a planet, you will have this signal detected in 30 days, or these are the ways, or the activity will be this way. Without that, it's pure speculation, and then there are all these papers that we have discussed over the few years with some of my colleagues here. Okay, almost done. Now, let's see how we hunt Proxima b, just a bit the story of the thing, how it happened. So the first thing to note is that detecting planets around red dwarfs, because they are smaller, it's up to 100 times easier than around a sun-like star, just because the ratio of areas is favorable. In the Doppler method, it's about 15 to 20 times easier. But another thing is that you have repetition of the same signal many times over a short period of time. So at the end of the day, in terms of telescope time, it's actually 50 to 200 times easier to detect small planets around red dwarfs. And now you combine this with the fact that we have seen before, take-home message, you have most of the stars are red dwarfs, most of the stars have small planets in short period orbits, and now planets around red dwarfs are way easier to detect. And this is where we are now. This is 2016, and we know that this. We didn't know that 5 years ago, even 3 years ago. It was not clear that the picture was that. So now it makes sense to go star by star. We also know the occurrence rates are of the order of 1. Almost all the stars show signals of having planets, as you will see probably later. So now it makes sense. Now we don't want to discover planets to make statistics on nearby stars. We want to know which planets are in each star, which planetary systems, and what we can learn from them. So that's kind of the change. This is what we did for Proxima, in a sense. So there were almost 300 measurements in 2012 of Proxima. Now there was Mikko Tuomi, my colleague, that does a lot of Bayesian analysis and finds signals everywhere, and actually look at signals in Proxima data and found 4 of them. 2 of them we suspect are instrumental or related to stellar activity. One of them, it has a period of 11.2 days, so it was a suggestion of a signal. We submitted the paper, it was not accepted, but it's fine. And there was another signal at 38-day period that we will see pretty soon if it's a planet or not. It might be related to rotation, because rotation is close to twice that value. Okay, so we tried to get more data. In 2013, 2012, we got 200 more observations of Proxima, very poorly sampling the orbital period for a number of reasons. So even with 400 observations, we couldn't tell what was going on there. We had plenty of evidence that there was some wobble. This is Proxima in red compared to a standard star. So you can see really that over even sequence of 11 days, you could see the thing going up and down. And that's what gave us the clue, OK, let's try to do this, but not over 11 days, but over 60 days. Then what we can clearly see if it's related to activity or not. So, and these are periodograms, which basically tell you if you have a time series where there is a preferred period. If you have a signal that goes over these thresholds, then you have a clear detection. And you see that with the data from pre-2016, we had more or less a detection, but not really convincing. So this is when we designed the experiment, the pale red dot experiment, which consists on using HARPS for 60 nights in a row, and then also monitoring photometrically the star with other telescopes to see if we can see which variability is associated with the stellar activity, which one is coming from the planet itself. So that's what we did. That's the data. We collected radial velocity measurements. Clearly, the periodogram also showed the period at the same predicted period. And now you combine the data all together, and yeah, the signal just goes above threshold. No question here. Now, it's a question of, is this a real signal or can be induced by stellar activity? We think it's not for a number of reasons, but basically because we clearly see the rotation effect on the radial velocities and several spectroscopic indicators, but we don't see anything at the period of our planet. So now this is where we are convinced that we have a planet, and that planet has these properties as you have seen. Okay, so now we can start to speculate. This planet is what we call the habitable zone, which only refers to the temperature this planet might have around Proxima. This is for comparison, the orbit of Mercury. That would be the orbit of Proxima b here, and the habitable zone is really close to the star because the star is so faint. I had some slides on the TRAPPIST system, but we don't need because Michelle is here, and we'll be talking about this tomorrow. Great. So then I can just tell you what we are going to do next. So in 2016, we did pale red dot, and now we think we have a good recipe to identify these planets. We have plenty of data on most of these nearby stars, so we only need to combine it, identify the proper or the signals that look promising, bet them with photometry, and then plan a strategy to really pull them out of the data. So 2016, we had Proxima. Now we have red dots, which is the same, but on more stars. So Proxima was here. Now this year, we are going to do the same on Barnard star, a binary in the north, and also Gliese 729, which is a catalog number, but it's the 7th nearest star to the sun, so you should know, given that you are here. Probably also Wolf 359, this is CN Leo, another famous star. So these are the resources that we are going to use. Carmenes also, Carmenes spectrometer, now it's performing down to HARPS-like precision. And it's a spectrometer especially for northern targets, it's very useful, but also we have a campaign in this summer, 100 nights on these stars. So Barnard star, Proxima again, because we think that's a second planet or maybe more, and a few more of them. Of course, people start to join up, so we are really pulling a lot of resources into this. So if you are interested to know more about this, drop me an email. In June 20th, we start observing again, probably involving semi-professional contributions from the public. OK, so I'm almost done. The only thing I want to say is that the nearby stars, especially the 5-parsec sample, which is a relevant one for maybe sending something someday, you can make a lot of population statistics, but these are the stars. There's not more than this. So don't think about, yeah, G-dwarfs are better. Well, there are 3 G-dwarfs in this sample, so we don't need to think about G-dwarfs in general. Just think about them as individual objects. I can put this slide somewhere. I'm preparing kind of a report on what we know about all these stars. More details for another day, but just a few colors. What you can see immediately is that most of the circles are red, because these are red dwarfs. The big circles are early type M dwarfs, so 0.2, 0.3 solar masses. The small dots here would be late type M dwarfs, like TRAPPIST, things like this, or LHS 1140. It's the new kid on the block. We'll hear about it later. Anyway, so when you have these stars, you can think about what each of the methods can do to find planets around these stars. And some of them already have planets. I didn't put them here. But just, for example, look at the transit. So we have 73 stars. That's it. That's what we have in the 5-parsec sample. We want to find as many planets as possible. So with transits, this is a plot, several things, but it doesn't matter. So the green line here, imagine that all the stars have one Earth mass planet in the habitable zone of the star. It's just occurrence rate of 1. So we just put that planet there and start to accumulate the probability of having a transiting planet. And what you find is that when you reach 5 parsecs, with a 73% probability, you should have one planet transiting a star. It can be an M dwarf or whatever. And these large drops here come basically from the brown dwarfs and the very late type Ms. These are the ones that contribute more to this probability. Probably Courtney will be talking more about this, so I'm not going more into detail. And that's the cumulative occurrence rate. So you expect between 1 and 1.3 planets detected with this method, but only one or and there are 73 stars here. OK, so that's the transit technique. With the Doppler technique, if you put all the stars in the sample, you get that you would need 16,000 nights of telescope time to find all the Earth's mass planets around nearby stars, but this is not realistic. However, what you realize here is that big jumps come basically from sun-like stars or even more massive, like Sirius, Procyon here, Tau Ceti somewhere here. Tau Ceti is one of these. Well, I don't know. Alpha Centauri. OK, if you take all the stars that require less than 10 days of telescope time to detect a planet, to reach a sensitivity under a number of assumptions, what you get is that you can do 37 of them in 100 days. And these are the M dwarfs, basically, and the mid to late M dwarfs. So with 100 days of telescope time, which means it can be done today, and it's already happening because several surveys, and now we have the dedicated surveys on M dwarfs, this Carmenes. There will be a Japanese survey. There will be Spiru also in the French-Hawaiian telescope. All these planets will be found if stellar activity can be dealt with and a number of things. But this can be found in an order, in a number of nights comparable to a year or two. Basically means that 2-3 years, number of qubits, all these planets will be identified, at least the 40 ones that are easier. If you spend a bit more time, then you get a bit more objects in a bit longer periods, but But yeah, even in 5-year timescale, you can get up to 50 systems. So really, for detection point of view, the Doppler technique is going to give you much of the thing. And this is for the direct imaging, and it's my last slide, because I see that I'm over time. Here, what I plot here is, let's see how I can explain. Angular separation, planet, star. I put this planet in the habitable zone, and the star divided by the diffraction limit of an 8-meter telescope at 1 micron. Okay? It's just a number to get a feeling of what's this. So you see that if you want to do high contrast imaging, you typically want to resolve things, means that 1 or 2 or 3 times, you want to see things that are 1, 2, or 3 times farther away than the diffraction limit. And this only happens over this green line. And of course, these are the bright sun-like stars, or even more massive. So Alpha Centauri. Also, when you go farther away, the angular separation decreases. So at some point, you lose targets even around G-dwarfs. So here, Alpha Centauri, Sirius, it's a good target for direct imaging of Earth-like planets. Epsilon Eridani, the common known people. Procyon, Tau Ceti, Epsilon Indi, and the last one, Omicron 2 Eridani. And that's it. So you have 8 of them. Don't need to plan an instrument that will detect planets everywhere. If you want to do direct imaging and high contrast, these are your objects. And basically, you have 4 or 5 accessible from the south, 4 or 5 accessible from the north. You don't need to think much about it. Now, there's a new family of techniques here that can access this regime, which is what I called, there are several names people is using. We have to settle down. Ignace knows what I'm talking about, to settle down for a name, which means combining high contrast imaging with spectral enhancement means that you use the fact that the planets have different spectral features as the star. So basically, you can get a boost of 2 or 3 orders of magnitude in the contrast. So in this regime here, you can also expect to detect the planets kind of in contrast in direct imaging. You have to play a trick, so it's not just a picture. You have to do a bit more. But then this includes most of the nearby M-dwarfs, at least the ones that can be done. About 19 systems can be done probably with this technique. And then below that, if you can use this spectral enhancement if you get lucky, but these systems are almost hopeless unless they transit, and you have a lot of them. So there's not much you can do there. So the techniques here give you different information. Transit is the best probably because it gives you a lot of things, and also then you can do characterization. But you will only find 1 or 2 within the 55 parsec sample. The velocity is a lot of detections, but then the amount of information is limited, of course. High contrast, you can do 8 systems, and you have plenty of information, of course. When you get the picture, you know everything. And then maybe high contrast with a spectral enhancement can give you about maybe 15, 20 more systems. There are other methods that can provide you additional information. For example, try to resolve or try to see the debris disk or the asteroid belt or the worm dust in these planetary systems. This will tell you where is the orbital plane, so that it's complementary to, for example, radio velocities, or even image the star and assume that the star is coplanar to the rotation of the star is coplanar to the planetary orbit, and that also gives you some information about the orientation of the orbit. And that's it. That's my summary slide. You can read it while we take questions, and thank you very much for your attention. Oh, yes. State your name and institution.
This is Mercedes Lopez Morales from the Smithsonian Astrophysical Observatory. You mentioned that you are seeing a signal at 38 days on Proxima B now, which could be another planet. Are you doing the photometric follow-up to see if it is activity? Because I can think that you can see it in the photometry if it is the rotation of the star.
Yes, the rotation is, the thing is that, so we don't know yet if it's a planet or not. In this summer, we do 100 days, so we should be able to cover at least almost 3 periods of, no, 2.5. Yes, the rotation period is 83 days, and half of it is 41. So, yeah, might not be never as convincing as Proxima B because of what it is, but the truth is that we already suspected it in Mikko's original work, and it's also in the high cadence campaign from last year. it also shows there all the time. So, and it's always 38. It's not 41 or 42 or 35. It's always 38. Yeah, well, we'll see. It's a bit more, that would be nice because it's a bit more separated, so then high contrast imaging techniques and things like this might help there. We'll see. There's also some evidence for something at very short periods. But we didn't use the high cadence data. We got 3 nights in a row, 200 measurements almost continuously monitoring the star, and you can see something going on there. But interpreting that data is more complicated because then you get instrumental effects at meter per second level, and it's not easy to believe what's there. But there's some evidence also of something. No. Yes, Savi here.
Avi Loeb, Harvard. Of course, the next important step would be to figure out if they have atmospheres, any planets that are found in our neighborhood. And one way to do that would be to look for the temperature contrast between the day side and the night side with JET WST.
Yes.
Can you comment on how difficult it would be for the different stars that you mentioned?
Yeah, so for the sake of simplicity, this is what I call phase curves. Phase curves of everything. It can be temperature features because the warm side of the planet will have a different spectrum as the dark side, and then over full orbit you will have first the reflected light is different, and also the thermal emission changes over the orbit. You can do the same game probably with spectral features over the orbit of several of these planets. But so for some of them, if they don't transit, that's the only way you can do anything at all. Because if they are not separated enough and you cannot resolve them, and yeah, so it might be possible to do it. We'll see. I think we will have to play with a couple stars first. Depends on how stable are the stars and how well we can calibrate the instrument, especially James Webb Space Telescope, I think, is the one that can do the job. Maybe some tricks with the spectroscopy can be played with a very large telescope and spectrometers. Yeah, so everything that falls into here, that's the only way to characterize the systems. Everything, yeah, these ones here, of course, you can also do high contrast imaging and spectral enhancement up here. And these systems here, you can also try to do phase resolved photometry or spectroscopy. So yes, but this is, of course, is an alternative technique or one of the candidate methods. I just put it in parentheses because we haven't demonstrated that yet. But you're right, you have the paper for Proxima. And I encourage you and Laura to look at Leutenstar, which was announced a month ago, but nobody noticed because they put the catalog number in the title instead of saying it's a star at 3 parsecs. So it's one of these. Leutenstar is somewhere here. Anyway, it has 2 planets. And we have independent confirmation of the 2 planets with Carmenes, for example. So it's very robust detection, too.
Duncan Forgan, University of St Andrews. That was a great talk, Guillem. I wanted to ask you a bit about astrometry. So you mentioned the very last point of the last slide that you're going to need a space mission and it'll take some time. We already have a space mission called Gaia. Is Gaia going to be of any use to you for, say, turning a minimum mass into a true mass? Is it going to be helpful at all for the 5 parsec sample, or do you need to go to the next level?
No. So here, so this is only to detect this fiducial 1 Earth mass planet in the habitable zone of the stars. Gaia cannot do that, even for the nearest stars. Actually, in astrometry, it's easier the brighter the star because then the planet is farther away. But then you need a very long time to see the full orbit. So you would need to take a star like Sirius or something more massive, Vega. Maybe you can detect. But then the orbit would be very long, and then Gaia is not long enough. So no, it's 1 or 2 orders of magnitude of Gaia to detect planets with astrometry. This is why I put also in parentheses, because if we have something like Theia, this is the inheritance of a local astrometric mission where you calibrate your focal plane very well or very carefully and try to get local astrometry done. In principle, looks feasible. We submitted a proposal. I was involved in the M4 and M5. Unfortunately, it was declined and Brexit might have something to do actually with it, and also some problems with its budget going up and down there are some issues that need to be sorted out first. So no, we need a specialized mission if we want to do astrometry and to detect planets with astrometry. These Earth-like planets, we can detect gas giants and Neptunes even, but not Earth's mass. Worm.
Hi, Sid Hegde, Carl Sagan Institute, Cornell. I was wondering if you have a good estimate of the density for some of these rocky planets.
Well, you will hear about that later when they explain about the ones that transit. When you have transits and radial velocities, you have a measurement of the size and the mass, and that gives you the mean density of the planet. Some cases where you have multiplanetary systems in transit, you can also infer the masses from dynamical interactions. So that will be tomorrow. Michel, Guillem will be talking about this. So some systems vary. These one or two that transit, which are more if you go a bit farther away. When you go to 15 parsecs, there will probably a dozen of them. For these systems, you will have both mass and radius. That's, for example, LHS 1140. That's Dave and Tim are here. They might mention that. So for that one is the first one that we have mass and radius. And then, yeah, you know the density. You know what kind of planet you have.